Hey guys, Buildzoid here, and today we're going to be talking about memory channels and ranks on consumer DDR4 memory, because I've basically had people ask me lovely questions like, can you run dual channel off a dual rank memory stick? And it's, and basically no you can't. So I figured a video like this is in order because as the channel gets more popular, the questions keep getting stupider. Anyway, and like that, I've probably taken care of all the bad questions. Anyway, let's get into it. So first up, memory channels. Memory channels, the easiest way to think of them is they're 64-bit connectors, not connections. This is, I think, the part that confuses a lot of people. They're connectors. And obviously, the difference between a connection and a connector is that a connection is between two connectors, but a connector on its own doesn't actually do anything until you plug something into it. So, 64-bit connectors, and they connect your CPU to your memory. So it looks a lot like, you have your CPU, and it's got its memory channels, and they're a bit too big in that case. So we've got channel 1, channel 2. That then connects to your that obviously sits in your motherboard. So that then goes through the socket into the traces of the motherboard. And then at the end of that, you get your DIMM slots. Um, and I was considering including talking about memory topologies in this, but I've already done a video about memory topologies in the past, and there's nothing really I would change about that, and so I didn't feel like tacking on 10 more minutes to the end of the video just to discuss memory topologies. But anyway, so, you have your two channels, or connectors. Your motherboard, for all intents and purposes, is basically a cable, at least for DDR4. If you go back far enough, then you'd actually have logic related to the memory on the motherboard, but these days with DDR4, your motherboard is very much just a cable. Similar to how like your HDMI cable connects a GPU to a monitor, your motherboard connects your CPU's memory controller to a to memory sticks, right? And you can plug in multiple memory sticks into any memory channel, which is why we have, of course, two DIMM slots here. So, uh, yeah, now what you need to know from a performance perspective about memory channels is that they have a maximum theoretical memory bandwidth, or more like, it's not really a maximum, well, it is maximum, as in you can't transfer more data than that, but it's just, well, whatever. So mem bandwidth is basically equal to the effective memory speed in megatransfers per second multiplied by 8 bytes. And you might be like, why 8 bytes? Well, because 8 bytes is what you get with 64 bits. If you look at ECC, then it works a bit different. Well, you still get 8 bytes of transfer, but the actual connection is wider. But that's why I said consumer hardware. ECC memory is servers. So, it's just like we're not actually here to discuss that. Anyway, so memory bandwidth is mega transfers per second times bytes, times your, 8 bytes. Now, the thing about this is that a lot of people think that their memory runs at 3200 megahertz. This is like, say you buy like a 3200 CL14 memory kit. It actually runs at 3200 mega transfers per second. It doesn't run at 3200 megahertz. Now, literally everyone, including memory vendors and me and motherboard BIOSes and other overclockers, refers to effective memory speed in megahertz, which is incorrect. We should be referring to it in mega transfers per second, but nobody does that. So, just get used to it. Everybody says the wrong thing. Like literally even motherboard BIOSes say megahertz, and it's incorrect. We should be saying mega transfers per second because DDR is, that DD stands for double data rate, so the actual effective memory speed is twice the physical clock speed of the memory. And so the actual clock that your memory runs at, like if you have a DDR4 3200 memory kit, it actually runs at 1600 megahertz. Yeah, which basically, if you were doing this calculation with megahertz, then you'd take your megahertz times 2 and then times 8 bytes again. So it really doesn't make that much difference. It's just like, it is worth noting, like, well, there is a lot of like diagnostic software where if you go into and check your memory speed, it'll actually read real physical clock instead of effective speed, which is why, like, if you run a 3200, a 3200 memory kit, and then go into CPU-Z, CPU-Z will tell you that it runs at 1600 megahertz, and that's correct, because it does run at 1600 megahertz. It's just that everybody calls it 3200 megahertz, just everybody refers to the effective speed as 3200 megahertz. So anyway, But yeah, with this, you can calculate your maximum memory bandwidth per channel. And this is where channels become really sort of important in terms of performance, is like, also this right here is not 100% efficient. That's why I earlier referred to it as theoretical maximum memory bandwidth. Because, yeah, memory is not 100% efficient, so realistically you're going to get somewhere around like 90% of this as your actual bandwidth. And that 90% I've just pulled out of thin air. So, don't quote me on that. It's not exactly well, depending on your timings, you're going to be closer or further away from 90%. And I'm not sure if in both cases above that or below that. So, yeah, it's not like I've actually done a test to know roughly how much inefficiency there is, because it's actually really hard to measure that reliably. So, anyway, but the thing is so you can get like 90%, and we do need to put the like in front of that. That is, here it is, that's my technical term. It's not literally technical, it's just... Anyway, because it's not literally 90, it's like somewhere around that. Because when we get to the memory ranks, I actually need to include the fact that memory is not 100% efficient, and 90 is a nice convenient number for that. So anyway, but basically what this means is that since this is your memory bandwidth per channel, and this is true even if your timings are pretty bad. Okay, like even at stock JDEC timings, you're gonna have like 90% efficiency. Now you can improve that efficiency as you get tighter timings, but it's still, it's not going to be some massive, huge improvement. So anyway, the thing is you can get CPUs with, anywhere between like, well, I've not seen a single channel DDR4 CPU, but I would assume that it exists. But you can definitely get anywhere between 2 and 8. With 8 being very much AMD's EPYC servers, so we're just going to ignore those exist. But Intel does have the LG3647, Xeon, what is it, W3175X, which is technically a consumer CPU because you can overclock it, or at least I consider it a consumer CPU because you can overclock it, and that goes up to 6 memory channels. So the thing is, for every memory channel you add, you literally just get this lovely number right here as a chunk of bandwidth. That you just get that. So, if you go 1 DIMM, well, if you put 1 DIMM here and 1 DIMM here, which that's sort of like, well, okay, no, I said we're not going to cover topology. Go watch the topology video if you want to cover that. So anyway, you put your 2 DIMMs into your memory, like you go 1 DIMM, right? Then you've got single channel running. You get this amount of bandwidth times 1. You add a second DIMM and you get this number times 2, so you literally double your bandwidth. If your CPU has a, high, well, now that side looks really freaking weird, but whatever. If you've got a quad channel CPU, well, you add 2 more memory sticks and you've got this times 4. If you don't use the 4th channel, well, you get this times 3, right? So basically, every channel you add, just whatever frequency you're running that, you just add extra bandwidth. So going from single channel to to dual, you get double your bandwidth, which basically means running a single stick of memory under all circumstances is a bad idea. Okay, you are literally cutting your maximum, well, not even, like, you are literally cutting your memory bandwidth in half if you run a single channel memory configuration. And the thing is it basically means like one channel of like 4266, or actually it would be, this is a better example. So 2 channels of 2133 memory is literally faster than 1 channel of 4000. Okay? Because with 2 channels, you get your, you take your 2133, plug it in there. It's effectively like 4266 on a single channel. So you really, really don't want to, like, running a single stick of memory is something you do when you absolutely cannot afford to run 2. Okay? It is not a good decision for performance, ever. If you want good performance, and this is especially true if you have something like an APU, where the iGPU is very memory bandwidth starved, where it's just like, yeah, if you run single channel, you're going to like take some 30% of your FPS and just throw it out the window, because that it's just bound to how quickly you can get data to the GPU. And well, if there's nothing for the GPU to process because you're running single channel and you can't move that much data, well, you're not going to get that many frames. So that's kind of the thing. So basically, as a sort of performance priority, you want to run as many memory channels as your CPU has. Once you've populated all of the memory channels, then it's a good time to start worrying about clock speed, because generally speaking, 2133 megahertz memory is a hell of a lot cheaper than even like 3600. And well, there might be certain, like, triple channel 3600 might actually be a better option than like quad channel 2133, but at the same time, that would be true for like Intel quad channel CPUs and not necessarily true for like AMD quad channel CPUs, because some of them have very strange memory controller configurations where it's just like, you just don't want to deal with it. So basically, unless you're desperate, run as many memory sticks as you have memory channels, because these are connectors, and if you don't plug a memory stick into them, then they don't do anything, and you lose this much bandwidth per unused connector. Okay, so there. That's the very simple version of memory channels. Now, other interesting things you can do with memory channels. So asymmetrical memory setups. For DDR4, these would be like 12 gigs, which I just strongly don't recommend. 24 gigs, which actually this can work. This can work. You just need to be a bit clever about it. I still don't like, if you don't know what a memory channel is, then I honestly don't recommend that you try to set up a 24 gig memory configuration, because you're gonna probably fail at it. I've done it. I've run 24 gigs at actually decent speeds, but it's kind of awkward to set up, and so I don't recommend it to most people, even though on paper it's actually not that bad an idea. 12 gigs, on the other hand, is a bad idea, and the reason for this, and then of course we get other, and this is depending, this of course depends on your CPU's memory controller. If you're on that Intel 6-channel Xeon, then 24 gigs is actually just fine, because that's one 4 gig stick per channel, so you're not going to have any issues. But obviously I'm talking about these setups within like a dual channel or a quad channel. Well, you wouldn't run this on dual channel, but you might run some, you wouldn't run this on quad channel, because it runs into the same issues that 12 gigs runs into, which we'll get into, but you might want to run something like 48 gigs on a quad channel CPU, and that's actually not necessarily, like, that works the same way as 24 gigs on dual channel. So, basically the issue with, 12 gigs and 24, like with 12 gigs, is that if you put 4 gigs of memory on one channel and then 8 gigs of memory on the other channel, the way the memory controller actually manages to double your memory bandwidth is, let's say you have, I don't know, 10 gigs of data that you're going to be doing work on, right? You want to process some 10 gigs of data. So your memory controller, if you have, 2 8 gig DIMMs, it'll put 5 gigs here and it'll put 5 gigs there. Everybody's happy, right? You share the memory equally between your memory sticks, and now you can access half of that data at, across each channel at the speed of that one channel. So this works just fine. Now, if you have a 4 gig stick and an 8 gig stick, then we run into a problem, because you need to put 4 gigs here and you put 6 gigs there, right? You split your 10 gigs asymmetrically. And the problem with this is now you have 2 gigs of memory, right? 2 gigs of data that you can only access across one of the 2 memory channels, which means that when accessing these 2 gigs of data, you're going to end up at single channel memory speeds. And there's nothing you can really do about it. Like, I'm not going to get into the details, but basically you just end up with single channel. So having a 12 gig memory setup is very bad if you actually go over your initial 8 gigs of memory, right? And then you end up in a really bad situation. Now, funnily enough, 12 gigs of data, like 12 gigs of memory in this awful scenario where, like, eventually it'll end up running single channel if you just keep using enough RAM, that is still better than hitting your page file, which is going to be on your SSD or your hard drive, because your SSD or your hard drive are still going to be, well, your hard drive definitely, but even your SSD, it doesn't matter what SSD you have, it is going to be far, far slower than even single channel memory. But nonetheless, I would strongly recommend against running 12 gigs of memory on a dual channel CPU, like in an asymmetrical, 4+8 configuration, because essentially you're going to end up with your memory performance randomly tanking within various workloads, and it could lead to, stutter and all kinds of other various sort of hard to trace issues, because it'll only show up once you start using enough of the memory that the memory controller can no longer evenly share the data across both channels, and then you end up with stuff that it takes twice as long to access it because, well, it's stuck on one channel, not on both anymore. Now, 24 gigs works because you can essentially run 24 gigs as just 4+8 and 4+8. Now, the issue here is electrically, so logically this works just fine because the memory controller has 12 gigs on channel 1, 12 gigs on channel 2, so it can share the memory between the two channels just fine. You're not going to run into, any weird performance issues, but electrically this is actually awkward to run because now you have two potentially very different memory sticks, and with potentially different memory chips, different PCBs, different layouts. And the problem with this is that you are potentially going to end up with massively reduced memory frequencies. Let's say you're targeting, I don't know, say 4,000 megahertz, okay? And individually, this 4 gig stick can do 4,000. And individually, this 8 gig stick can do 4,000. But if there's a big enough mismatch between these two memory sticks, you put them together, you might be stuck at 2133 or 2400. So you're going to lose a huge amount of clock speed if you mix the wrong set of memory sticks together. But in a lot of scenarios, this can actually work just fine. You just kind of need to be a little bit careful with what memory you use to do it. So yeah, like the main thing with the memory channels is just like you want to make sure all your memory channels have a memory stick. Okay, that's really good for your performance. Having a memory stick, very important on the channel. B, that all the memory sticks are the same size. Otherwise, you're going to end up with sort of weird performance issues. And even then, it's like, not having the same size memory sticks is not a disaster, is not as bad as running out of RAM. Okay, so it's like if you are being on 8 gigs of RAM and literally running out of memory sucks far more than having 12 gigs of RAM and running, single channel mode occasionally. At the same time, I would strongly recommend you just go straight for 16 gigs, right? Because running out of RAM is like, if you end up in the page file, it just sucks. And if you run in single channel, then things still suck pretty badly. Yeah, so that's kind of all you need to know about memory channels. They're connectors. You want to keep your memory, you want to have every channel with the same amount of memory, and your memory bandwidth is basically this right here multiplied by however many memory channels you actually have populated. So then let's move on to memory ranks. Memory ranks were created to add capacity. And the reason why I feel this is worth specifying is because that was the primary purpose of creating memory ranks. It was just a method of adding more capacity, because if you have your CPU, and you have your 64-bit wide memory channels, so each channel is 64 bits. Now you can get memory chips in, we'll have our... Actually, so you can get memory chips in widths. So IC, so integrated circuit memory chip. That's what that stands for. So mem chip width is basically, you can get memory chips that come in a X4, X8, or X16 memory width, which basically refers to how many bits each memory chip connects to. So if you have a X16 memory chip, you can attach 4 memory chips to a single 64-bit memory channel. And the problem with this is, of course, well, let's say we have this this theoretical memory chip right here, right? And it's going to be 4 gigabits of capacity. For whatever reason, memory chip capacities are specified in gigabits, not gigabytes, but doesn't matter. You just it just means that you need to divide the capacity by 8 to get bytes. Anyway, so 4 gigabit, and it's an X8 memory chip, right? So if it's an X8 memory chip, also these X4 chips, those are server hardware. So I'm mentioning that they exist so that you don't, like if you see an X4 memory chip, you don't get confused, but they don't work on consumer CPUs. So you can just kind of ignore them past that as far as, well, I ignore them past that. It's just like they exist, but you're actually never going to run them. And X16 is primarily meant for like high density applications where you don't want to have a bunch of memory chips physically taking up a lot of space, because with an X8 memory chip, well, you're going to need 8 of them. Right, like you need 8 of them to connect to the memory channel, because unfortunately you can't run DDR4 memory channels in 32-bit mode or 48-bit mode. It doesn't work. They only run in 64-bit mode, so you need to hook up 8 memory chips to each channel. So we have this 4 gigabit X8 memory chip, and so obviously we use 8 of them to make a memory stick, and that gives us that gives us a 4 gigabyte memory stick. Now, the problem with this is like, okay, so we can stick our one 4 gig memory, so we can stick our one 4 gig memory stick onto channel 1 and another on channel 2, and now comes the question of like, well, how do we connect another 8 memory chips? Right? Like, what if you want to run more than 8 gigs of RAM? How do you get the memory controller to work with more memory chips if we only have a 64-bit wide bus and we've just connected every single link in that connector to a memory chip? Like, how do you add more memory chips? So the solution that the CPU manufacturers and memory manufacturers came up with was called the memory rank, which basically is just like this right here is one rank. Any group of memory chips that makes up that basically adds up to 16 bits, 64 bits of width, is a single rank of memory chips. It's one rank. And basically, it's just a grouping system for memory chips, so that the memory controller can basically go and hey, I want to talk to this group of memory chips or that other group of memory chips or the next group of memory chips. And on consumer hardware, you can go up to 4 ranks. So consumer is up to 4 ranks. And you can't run more than this because electrically it's just not very... Like, electrically, more memory chips hooked up to the same connector just starts causing major, major issues, so the CPU manufacturers just restrict you to only using 4 ranks of memory. Server hardware can go way past that, but consumer DDR4. So, I don't care about server hardware, you can't overclock it, so not part of this video. So you can go up to 4 ranks, and each rank is just a group of memory chips that is, 64 bits in total. And so with X16 chips, that would be 4 chips. With X8 chips, that would be 8 chips. Now, X16 you will occasionally find on very low-end memory because sometimes it just happens to be the cheapest stuff on the factory floor that day, and they'll make a bunch of desktop DIMMs with X16. But generally, if you're actually buying like good, higher-priced desktop memory sticks, they're going to be using X8 chips because that's just normally what you use for the higher end memory sticks. I'm not sure if there's like a major binning issue, like if there's some kind of major issue with the X16 chips. It's just like I've never seen a high end memory stick using them. I don't know if that's because they're bad for high frequencies or if it's just because laptops are the primary use for them, and so nobody really wants to bother with like binning them for desktop applications. Anyway, so each rank is basically just one group of memory chips. Now that makes up 64 bits, and now you can go and just take 4 groups of it. Like you can make 4 ranks. You can put 4 ranks of memory onto channel 1, so you can have group 1 of 4 gigs, group 2 of 4 gigs, group 3 of 4 gigs, and triple rank is a thing. It works just fine. And of course, group 4 of 4 gigs. And then you have 16 gigs of memory on channel 1, and then you can do the same thing on channel 2. Ranks are specific to a memory channel. If you have 4 memory sticks with 1 rank of memory each, and you plug them into a dual channel CPU, you have 2 ranks across, you have 2 ranks on each of your 2 channels. You don't have 4 ranks in total because the ranks are within a memory channel, right? Like, they were created to add capacity to a memory channel, because otherwise you would just need to add more memory channels, which gets really expensive really, really quickly. because then your motherboard needs to now connect like way more DIMM slots to the CPU, and well, you also take up space on the CPU die itself for the memory channels. So memory channels are very expensive. So memory ranks were created where it's just like, look, you can just plonk another group of memory chips onto the same memory channel, and that's called a rank. Now the CPU manufacturers. Now, you may remember how I mentioned memory is not 100% efficient. Well, the CPU manufacturers got a great idea. Because memory is not 100% efficient, it means that the actual connection, the wires that connect the memory stick to, not even the memory stick, the rank, that connect the rank to the memory controller, they're not going to be used 100% of the time. There's not always going to be data moving across the motherboard to and from the memory sticks. So the CPU manufacturers were like, well, these wires just go to every single rank, ultimately. Like, all the ranks share the same set of wires. That's part of why you can only go up to 4 of them, because if you keep adding them, the wires start getting too long, and it starts causing issues. But the CPU vendors basically were like, well, if the wires are unused, but we have a whole second group of memory, let's say you just have a dual rank setup. Well, there's group 1, you have rank 1 and rank 2, and the wires are not being used by rank 1, right? Let's say you're trying to read something from rank 1 and rank 1's not ready to do that right just yet. Well, you could just go and like write or read something from rank 2 while you're waiting for rank 1 to do whatever it's doing. And that's called rank interleaving, and it basically boosts your memory efficiency a little bit. So you still can't get it quite up to 100%, but if you go from like one rank, you might get 90%. One rank might be like 90% efficient. Well, from that you can go up to 2 ranks and you get like 95% efficient. So basically at the exact same clock speed, at the exact same timings, you get like 5% more bandwidth, which I'm pretty sure is actually way too much, but you get the idea. You get a little performance boost. And I'm saying way too much as in I think 5% is actually too much of an increase. I'm pretty sure it's more like, it might be lower. I'm pretty sure it's lower. So going from 1 rank to 2 ranks, you get a bit more. Going from, 2 ranks to 3 ranks, you get a little bit more, say 97%. Actually, not even. You get like 96. Yeah, okay. There. We need to make this progression better. So you go from, 90 to 94, then to 96, and then from there, you go up to 4 ranks, and your efficiency hits a peak of like 97%. You can't actually hit 100% memory efficiency. It's just not possible. But you can get very, very close. And with 4 ranks, you get very, very close to that. Now, the downside to having lots and lots of memory ranks is they absolutely torpedo your overclocking capacity, because you now have much longer wires connecting many more memory chips, and the actual sort of interface that like the memory controller of the CPU has to be able to drive the interfaces of the memory chip. So you basically start losing frequency as you keep adding ranks. Now, admittedly, your performance per clock improves, but notice how this right here, this is like plus 4%. Right, and on 1 rank, depending on the CPU, well, let's say Intel, if we talk about Intel platforms, because AMD platforms are a bit strange, so we're not going to get into that. I have videos covering other AMD memory overclocking stuff. You should just search for them. But on Intel platforms, like Z390, 1 rank, you can probably quite happily run 4400, maybe even higher frequencies at decent timings. And if you go from 1 rank to 2 ranks, very quickly you'll find that now you can do like 4,000 megahertz. Well, I mean, mega transfers per second. See, everybody does it. If it's 4,000, it's not 4,000 megahertz, it's 4,000 mega transfers. But anyway, so from 4,400, you'll end up going like 4,000. Then you go to triple rank, and I've never run triple rank on Intel, so I actually have no idea what it does on Intel platforms. On AMD platforms, it actually works relatively okay, but you do lose like 100-ish megahertz compared to dual rank. So, yeah, I ultimately don't know what it does on Intel. Probably, like, Intel's memory controllers are kind of sensitive to doing weird things, so you're I honestly, yeah, like I'd expect it to probably end up at like 3733 or something. And then, of course, at the end of that, you've got like 3600. And the problem here is, of course, well, going this way, you get plus 10% more clock speed. So, it's just like, yeah, at 4000 with dual rank, you get 4% more efficiency, but on single rank, you can literally just clock 10% higher and get, like, overall your performance ends up being higher because your frequency is so much higher. Now, obviously, this is kind of nitpicky because we're talking about very small percentage increases in performance in memory performance, where memory generally, like, doubling your memory bandwidth will in most workloads will not translate to a 2 times speed increase for the workload, as in something that took an hour at 4000 megahertz is not gonna, I mean, at 21, something that took an hour at 2133 is not going to take half an hour at 4266. There are very few workloads that scale that well with memory. And obviously, I'd say the priority for most people is, of course, the capacity issue, right? You just add capacity. That's the main benefit of having more ranks of memory. So, rank interleaving is just kind of like a neat side effect of if you're running a, say, 4x8 memory configuration or a 2x16, because the thing is you can obviously fit multiple ranks of memory sticks onto, multiple ranks onto a single memory stick. Because, as I mentioned with the memory channels, you can attach 2 memory sticks to a memory channel, but how do you get 4 ranks onto a memory channel if you can only attach 2 memory sticks? Well, you can put 2 groups of memory chips onto a memory stick. So if you've ever seen a DDR4 memory stick, normally you have memory chips on one side. If you have a dual rank memory stick, then you'll have, if you have a dual rank memory stick, you'll have memory chips on both sides. That's all there is to it. And then you're going to have like rank 1 and rank 2 on the same memory stick. And you plug this into a channel, you get dual rank. You plug 2 of these into a channel, you get quad rank on that channel. Now, there is a interesting exception to the... So you can get like single rank DIMMs, dual rank DIMMs, and that's the standard rankiness of memory sticks. But Asus and G.Skill and Zadak basically had this genius idea of, hey, what if we just cram 4 ranks onto a single memory stick, because Asus wanted to offer higher memory capacities on their mini ITX and extreme overclocking motherboards. And the solution they came up with was, well, if you just make the memory stick really tall, you can put more memory chips on it, which is just like, yay! And so that's the, DC DIMM, double capacity DIMM, as I think that's what that stands for. Though, funnily enough, you can actually get higher capacity DIMMs these days in dual rank, because these were designed for 8 gigabit memory chips. Like, Asus came up with them for 8 gigabit memory chips, but these days you can get 16 gigabit memory chips. And I've not heard of a 16 gigabit DC DIMM, but you can get like 16 gigabit dual rank DIMMs, which are 32 gigs a stick. So these were basically 8 gigs, 8 gigs, 8 gigs, and of course 4 ranks of memory chips. I'm not sure what the order is. And the way these work is basically they trick the... Because the funny thing is, the way the actual CPU identifies different memory ranks is it doesn't identify them as rank 1, rank 2, rank 3, rank 4. It basically identifies the groups of memory chips as DIMM, first as a memory stick, and then you have basically DIMM 0, rank 0, or you have DIMM 1, or, well, you'd have DIMM 0, rank 1. Right, so you can have DIMM 0 rank 0, DIMM 0 rank 1, and then for your second channel you have DIMM, not second channel, but then on that same channel you would have DIMM 1 rank 0, DIMM 1 rank 1, and then and that's specific to that channel. So you basically have like a full identification for of a memory rank would be something like channel 1, or actually it would be channel 0, DIMM 0, rank 0, right? And then you'd have channel 0, DIMM 0, rank 1. And then channel 0, DIMM 1, rank 0. And you go through that like that, and then, you'd have the same thing for every single memory channel. So the funny thing about these DC DIMMs is actually, from the CPU's perspective, this is 2 memory sticks. It's not 1 memory stick, it's 2. But it's mostly just like how the identification system works. It doesn't actually impact the... it doesn't really matter, because this is just the system that the CPU uses for identifying different memory ranks, and I guess it made it kind of awkward for Asus to make these work. But Yeah, basically, so that's memory ranks. They're primarily there to add capacity, but they do have an interesting side effect of boosting your memory performance at the same clock speed. As a side effect, they sacrifice your clock speed. So if you add enough ranks, your memory efficiency might be really high, but your overall clock speed will be so low that overall you end up losing performance. There are, of course, platforms where you can't actually clock that high in the first place, and even at high rank counts, you actually get similar clock speeds. And on those platforms, it just makes sense to run more ranks. And the way you get triple rank is if you take a dual rank DIMM and mix it with a single rank DIMM. So, yeah, you take two, you put those two together on a channel, and you get triple rank. So, yeah. That's everything there is, and in terms of performance importance, basically max out your memory. Well, no, first get your correct memory capacity. Get as much RAM as you need, because if you hit the page file, life is gonna suck, okay? Like that is, page file sucks. Don't go to the page file, have enough memory. So first up, get the memory capacity that you need. Secondly, get it in a configuration that isn't single, like get it in a configuration that you're using as many memory channels as you have. So if you have like a AM4 or LGA 1151 or LGA 1200 CPU, 2 memory sticks. If you've got, LGA 2011-3, also known as X99 or X299 or X399 or TRX4, is it TRX4? Or, well, TRX40, right? You want to get 4 memory sticks, at least, because that way you get your quad channel. And then if you've got the Intel 3175X Xeon, you get 6 memory sticks. And then if you still don't have enough memory capacity, well, you get twice as many memory sticks, unless you want to start messing around with, these kinds of fun memory combinations, which could, like, especially, I guess, like 64 gigs of RAM is pretty damn expensive, and 48 gigs of RAM would be a decently cheaper alternative. And I guess if you run out on 32 gigs, then 48 gigs is a great idea. And personally, I actually ran 24 gigs daily for a while. It sucked, though, because two of the memory sticks were really, really bad, and 2 of them were pretty damn good. Like, I had 2 good sticks and 2 terrible sticks, and so overall it just sucked. But yeah, like 24 gigs is actually can be a very cost-effective alternative to 32 gigs, because 16 gigs of RAM gets a bit small pretty quick, but 32 gigs of RAM in a lot of scenarios is just kind of way too much. But ultimately, like, get the capacity you want, then start worrying, get the capacity, channels, then start worrying about sort of frequency and ranks. And I would honestly say prioritize frequency, unless you're on a platform where on dual rank you can hit the same frequencies as a single rank. And a platform like that would be AM4, because Ryzen's memory controller is a mess, and so going above 38, like going above the frequency of your Infinity Fabric just doesn't make any sense from a performance perspective, so you're better off running like dual rank at like 3600 or 3733 or whatever Infinity Fabric clock you can do. You want to run that dual rank or triple rank or quad rank. I'm actually not even sure. Like, well, I've heard that apparently with some memory sticks you can do quad rank in like 3600 on Ryzen, or maybe even more than that. But I don't test quad rank memory setups because they're really, really expensive, right? Because you're just like, ultimately these days, if you're looking at quad rank, you're looking at least 64 gigs of RAM. And it's like, yeah, that's a bit much. I have no use for 64 gigs of RAM, and it costs way too damn much, so I just don't test it. So, yeah, anyway, so capacity, channels, and then you can start worrying about frequency or memory ranks, once you've got the right capacity and all of your memory channels populated. So yeah, that's it for this video, and hopefully with this I will no longer get questions from people about, like, can I run 1 memory stick in dual channel? Because, like, somebody actually thought, like, they basically were like, can I run this in dual channel? And it's like, well, do you see 2 connectors on this memory stick, sir? Because I sure don't see 2 connectors, so I don't know how you're going to plug it into 2 memory channels at the same damn time. And hopefully I won't get any more questions like that. Which, there, I actually finally answered that question. Just like, it's not 2 connectors. And it's like, Yeah, anyway, so yeah, that's it for the video. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with Actually Hardcore Overclocking, I have a Patreon. You can support me through that directly. There's a link to that down in the description below. Other than that, there's also the AHOC Teespring store where you can where you can pick up shirts, stickers, posters, the usual YouTuber merch stuff. So yeah, if you'd like to help out with running the channel through that, there's a link to that down in the description below as well. And yeah, that's it for this video. Funnily enough, I've technically done a video about memory ranks in the past, but I figured it would just make sense to also include it after the context of what a memory channel is. So yeah, hopefully this makes sense. I've shot this video so many times and I didn't like any like, well, I don't even like this take. This is just such a stupid topic in my opinion. It's just like, you could just go to Wikipedia and it'll give you the bloody answer. Why do I have to make a video about it? Anyway, yeah, goodbye. I'll hit the stop button before like I decide not to record, like not to post this, because at this rate that we're getting there, definitely getting to the point where I'll be like, I'm actually not posting this one. Anyway, yeah, goodbye. I'll actually hit it now.